So the internal resistance of a battery, which is what leads to that battery using up some of its voltage push before the voltage push even gets to the terminals, that's represented as a little resistor with lowercase r, and then the battery symbol, and then there's a dotted line around the pair. So if you see a circuit drawn out like that, then you know that this is going to be a question to do with lost volts. So this formula kind of makes sense. The total voltage from the battery equals the voltage lost to the battery plus the voltage left for the circuit at the terminals of the battery. Now we've got a formula here which essentially says voltage equals voltage plus voltage, and that would be potentially confusing, so we give different names to the different voltages. So total voltage, we give the name EMF. The voltage lost to the battery itself is what we call lost volts, so that gets the voltage word, and then the voltage left for the circuit at the terminals of the battery is known as terminal potential difference. This formula then evolves into EMF equals I times little r plus I times big R. So I times little r is the lost volts, and I times big R is the terminal potential difference. Now sometimes you use part of this equation, so sometimes you can just say lost volts equals IR, or sometimes you just say TPD equals I big R, but sometimes you have to use all of the equation. It's not unusual for you to have to use all of the equation as a first step in order to find current, and then as a second step you can just use part of it, because now you've got current, you can find either lost volts or terminal potential difference. So remember, the more work you do, the more money you lose to tax, and the more stuff you want the battery to power, the more currents you're asking the battery to push around, the more the lost volts are going to be. And if lost volts are getting bigger and bigger and bigger, then the voltage left for the terminals, in other words terminal potential difference, is going to get smaller and smaller and smaller. So what we can do is we can it's usually a very simple circuit, and we are asking the battery to provide or to push around more and more and more current. So current goes up and up and up. As we are asking the battery to do more and more and more, then more and more and more voltage is lost as lost volts, and so the terminal potential difference goes down. So here's the current going up, here's the terminal potential difference going down. So there's a few, if we plot this graph, there's a few things we can read out. When there's no current at all drawn, then nothing is lost as lost volts, and so the terminal potential difference is the same as the EMF. It's always a downward slope, and where the slope cuts the current axis, you can see that that's going to be the maximum current condition. Now in reality this slope is pretty shallow, so in reality you don't have enough space on the page to extend the current axis in order to read off this short circuit maximum current condition. The reason it's called short circuit is because how you achieve this in real life actually is if you want to get this maximum current, you want the external resistance in the circuit to be 0 ohms, and I suppose you never get it exactly 0, but the way you get it virtually 0 is you attach a very short length of wire just between the battery terminals, and that's called a short circuit, and you get a very big current, and it is really bad for the battery. So normally you can't actually read that off the graph, so if the question asks you for short circuit current, then you use the formula which was on the previous slide, but you stick in capital R equals 0 ohms. If you've plotted this graph, then in order to get little r, which is the internal resistance, you find the gradient of that straight line, multiply it by -1, because the gradient's negative, and if you multiply something negative by -1, then you get something positive. Make sure you put this line of working in. For whatever reason, the SQA are very hot on it. Right, moving on to capacitors. So let's say you want to build a taser. The police force carry tasers now. They're those yellow gun-shaped things, but they don't shoot bullets. What they shoot out is a little steel prong, and there's a wire which trails behind, and it's actually part of a circuit. So here we've got PC McPlod, and here we've got Dodgy Geezer, and PC McPlod fires a taser out at Dodgy Geezer and hits Dodgy Geezer with a huge amount of voltage, and he goes down. So it's not feasible to make this happen with a battery. You obviously need a source of voltage to make this happen. You need a source of voltage to knock down Dodgy Geezer, but a battery isn't feasible. Yes, car batteries can give you a very educational shock, but obviously car batteries are big and heavy, and the gun would be extremely unwieldy if it was powered by a car battery. What you want is you want to dump a huge amount of energy through something in a very, very short amount of time. Batteries don't do this. Batteries are like marathons. They give you a nice steady voltage push for a long period of time until they run down. That's not what you want here. You want a big dump of energy through something in a very short amount of time, and for that we use a voltage source called capacitors. Capacitors have a circuit symbol like that. Capacitors store energy electrically rather than chemically, and because a battery stores energy chemically, then it takes time for that chemical reaction to happen, which creates voltage, whereas because a capacitor stores its energy electrically, then that voltage pressure is always there. You don't have to convert it from chemical energy to electrical energy. That electrical energy is already there. We don't need the energy conversion. So how do we charge a battery? How do we charge a capacitor up? Well, a capacitor is two metal plates separated by an insulator, although the metal plates are often more like aluminium foil, with some sort of like cardboard insulator in between, and sort of wrapped up tightly in a cylindrical shape. So they're not very often actually big metal plates these days. But here's a battery. We know that the battery pushes current around, it pushes electrons round from negative to positive. So here's the negative end. It pushes electrons round. The electrons pile up on the plate, one of the plates of the capacitor, and the electrons here repel off electrons from the other plate, which leaves this plate very, very positive. So you've got something with a very negative side and a very positive side, and hey, that's voltage, isn't it? So now we have a circuit, and we fire out two prongs, and they stick in what we call them, Dodgy Bob, whatever. And now Dodgy Bob is in part of the circuit. So this capacitor, the negative plate, pushes current around the circuit and through Dodgy Bob. The middle bit is an insulator. An electric field can exist across it, but the electrons can't move across. So in the charging circuit, if the electrons can't move, if they're blocked, then the current drops down to zero, doesn't it? Because it's kind of like hit something it can't go through. So in the charging current circuit, it goes down like that. The charging voltage goes up like that. The voltage push of the capacitor gets bigger and bigger and bigger. When the voltage push of the capacitor is the same size as the voltage push of the battery, then there can be no net voltage push, because the push forwards is now being cancelled out by the push backwards. So that's why a capacitor can never be charged to a greater voltage than the battery used to charge it. And so this horizontal part, is always going to be the same as if this is the capacitor voltage, this horizontal part, this maximum voltage of the capacitor is going to be the same as the voltage of the battery used to charge it. You'll notice it's not a straight line, it's a curve, so it's quite easy for the electrons to be pushed on at the start, but as more and more electrons pile up, the repulsion from the electrons, the voltage pressure going in the other direction, makes it harder and harder and harder for further electrons to be pushed on. So that's why the slope, the gradient, gets less and less and less. For the discharge graphs, the current gets pushed around in the opposite direction. So current is, in a sense, a vector quantity, so it matters which direction it's moving in. So that's why the discharge graph starts out very negative, But again, then current drops down very quickly, and this is the thing about capacitors. This time period here is very, very short. You want to dump all of the energy through something, maybe the dodgy geyser, in a very short amount of time. So you get a huge amount of energy dumped through something in a very short amount of time, and the voltage drops off very quickly as well. So a capacitor is all about storing separated charge. We've got negative charge on that plate, positive charge on that plate, and this is a charging circuit, we know. So if you're all about storing electric charge, then it's important to have a notion of how much electric charge Q can you store, because the more electric charge Q you can store, the more energy you can dump through something. So if you're designing capacitors, it's all about how much charge can you store. So the storage ability of a capacitor, storage space of a capacitor, is called the capacitance. Capacitance, capital C. Capacitance is measured in farads. So the storage ability of your capacitor is one of the factors in terms of how much charge Q can you store. The other factor is how hard can you shove these electrons on. And obviously, how hard can you shove them on is the voltage. So if you've got a bigger voltage charging battery, then you can shove on more electrons, and so you get more separated charge Q. A good analogy is if you've got a wardrobe and you're wanting to fill it with dancing shoes. The bigger the size of the wardrobe, the more shoes you can fit in, so that's capacitance. But also, if you can push and cram, the harder you can push and cram shoes in, the more shoes which are going to be stored in the wardrobe. So the harder you shove them in, the harder you push, the bigger the voltage, then the more shoes you can store. If you have a charge voltage graph, then as you push more and more shoes into that cupboard, then more and more shoes will fit in. And it's the same thing. The bigger and bigger voltage you use, the more and more charge you can shove onto a plate, however much the plate starts repelling. And the gradient here is the capacitance C. So if you've got a bigger capacity wardrobe, then for a given size shove, then you can fit more shoes on, or more shoes in it. Now you might recognize this as a straight line graph. Now the equation for a straight line graph is y equals mx, but replacing y equals mx with the variables in here are q equals cv. So this is one of the formulas on the formula sheet to do with capacitors. Also, the area under this graph is the electrical energy which is stored, and these are the formulas, and these are on the data sheets, on the formula sheet. If you have a bigger capacitance capacitor, let's say your taser needs a lot more energy, let's say you want to pimp your taser and you want a lot more energy to be stored, then you will swap out your capacitor for a bigger capacitance capacitor. So how would that affect the shape of the graph? Well, your bigger capacitance capacitor will take longer to charge up, because it's like having a much bigger wardrobe. It's going to take longer to fill with shoes. Now, yes, you're not going to get that capacitor to any greater final voltage, but unless you change the battery, but you're still going to get a lot more charge Q stored, and so you're going to get a lot more energy. If you were to decide to randomly whack a resistor in the charging circuit, then the charging up would take longer as well. So you get the same shaped graph as if you had a much bigger capacitance capacitor. So if you were to put randomly a resistor in the charging circuit, it would be like having the same size wardrobe as original, but I don't know, having like, sounds strange, but like having a bog or a swamp in between you and the cupboard. It would take longer for you to fill